This is MSJ Chem. In this video, I'll be looking at Graham's law of effusion. We'll start with a quick review of kinetic molecular theory. According to kinetic molecular theory, the absolute temperature in Kelvin of a gas is directly proportional to the average kinetic energy of its particles. Therefore, two different gases at the same temperature have the same average kinetic energy. The average kinetic energy of a gas is equal to half the mass times the average velocity squared. For two different gases, A and B, half times the mass times the velocity squared of gas A equals half times the mass times the velocity squared of gas B. If gas B has a higher molar mass, to have the same average kinetic energy as gas A, the average velocity of the particles must be lower. So at the same temperature, heavier gas particles have a lower average velocity than lighter gas particles. Next we look at effusion. Effusion occurs when a gas escapes through a small hole in a container. Graham's law states that the rate of effusion of a gas is inversely proportional to the square root of the molar mass. Here we have the equation for Graham's law, which is given in the data booklet. For two gases at the same temperature, the gas with a lower molar mass will effuse at a faster rate than the gas with a higher molar mass. This is because gases with a lower molar mass have a higher average velocity and are more likely to pass through a small hole in a container. Next we look at an example. Determine how many times faster H2 effuses than O2. So the rate of effusion of H2 to O2 equals the square root of the molar mass of oxygen divided by the molar mass of hydrogen, which equals 3.98. So H2 effuses 3.98 times faster than O2 at the same temperature. In our next example, we'll determine the molar mass of an unknown gas. An unknown gas effuses 0.25 times as fast as helium. Determine the molar mass of the unknown gas. So the rate of effusion of the unknown gas X to the rate of effusion of helium equals 0.25, which is equal to the square root of the molar mass of helium divided by the molar mass of X. By rearranging and solving the equation, we get a molar mass for X of 64 grams per mole.